Okay, thank you. This is a joint work with Jacopo Donnini and Valeria Corinaldesi. We come from Polytechnic University of Marte, quite close to here in Ancona. The use of fiber-reinforced cementitious matrix (FRCM) is a promising technique for retrofitting strengthening of structures of any material, concrete or masonry. But the weak point for this kind of application is the bond strength at the yarn-to-matrix interface. Indeed, often these systems fails because of the bonding at the interface. And so the aim of this study is to investigate the interface behavior and FRCM failure mechanism more in general, so the bonding and slippage at interface, but also fracture of constituents of matrices, in the matrices or in the yarns. And this study is carried out with experiments and with modeling. We have done pull-out test by considering different yarn, dry and coated, and different embedding lengths. And from the modeling point of view, we have developed a variational smear-cut model, which is based on incremental energy minimization, which is capable of capturing the bonding at interface, but also fracture in the constituents. Okay, these are the two different carbon fabric that we have considered, the dry one here and the coated one here. It is highly impregnated with an organic resin, and in such a way the interface bond strength increase a lot. This is the reason for this coating. We are going to consider pull-out test, so we are going to consider just one yarn, one dry carbon yarn and one coated carbon yarn. And here there is the experimental setup for the pull-out test. This is the yarn which is embedded in these matrices, in the cylinder, which is made of commercially available cementitious mortar, mortar 45. And we have considered two different embedding length, 20 millimeters and 50 millimeters. Okay. And at the moment here we impose a displacement, a tensile displacement, and we measure the force. And what we have are these force displacement response curve. This is the case of dry carbon yarn, and the behavior is quite brittle. Indeed, once, and these are the diagrams for H equal to 20 millimeters, and this one for H equal to 50 millimeters. And in these very short softening branches, we have the failure of the system, and in this case, failure occurs by interface debonding and slippage, while for a larger embedding length, failure is due to fiber breaking. And so these two different failure mechanisms depending on the length H here. In the case of coated carbon yarn, the behavior is ductile, as you can see. Well, first of all, the force peak load is larger than in the case of dry carbon yarn. And then here, both in the case of H 20 millimeters and in the case of H 50 millimeters, we have this softening which corresponds to the bonding at the interface. And then this very long stress force plateau which corresponds to slippage. And the system is capable of carrying forces because of friction, basically, at the interface. Regarding the modeling, we have considered a 2D geometrical scheme So we consider only 1/2 sample because of symmetry, and in this 1/2 sample we consider this section, and we impose in this section plane strength state. So this is the matrix domain, this is the yarn. We impose this displacement, and we consider with this lambda the interface. And the energy that we assign to the system are the following. For the matrix and the yarn, the energy is that of a linear elastic brittle material, and thus the energy depends on the displacement u, on alpha, which is the damage parameter, which is equal to 0 when the material is sound and equal to 1 when it is totally damaged. And here we have these two contributions. This is the first one, the elastic energy, and this second contribution is the damage energy, which has a local term, alpha, and a non-local contribution as well, which depends on the gradient of alpha. And here the constitutive parameters are this d, which is related to sigma e through this formula, and sigma e is the tensile is the normal stress at the end of the elastic stage, so it's the maximum normal stress. And L is an internal scale which is related to the thickness of the process zone. And here for the matrix we assume a process zone P equal to 5, which typically is equal to 2-3 times the maximum size of the aggregates inside the cementitious matrix. And for the yarn, B is equal to 1. The energy of the interface between matrix and yarn is a bit more complex. Here we have the elastic energy, which is a quadratic expression of delta. Here delta is the displacement jump at the interface. And then we have this damage energy, which is wholly local, and the damage energy density, W, has this expression basically, which is non-linear and which depends on two parameters, Q and A. A is related to the shear stress peak value, which is tau E here, and to K, and K is the elastic coefficient of the springs. And Q is related to the behavior at softening. Indeed, if we plot the diagram tau versus delta, for different value of Q, we can capture this different behavior. For Q equal to 2, we have a constant stress plateau, while for Q equal to -2, we have this brittle behavior. And for values in the middle, we have softening with different slopes. And so for the dry yarn, we assume Q equal to -2 to reproduce the brittle behavior, the brutal failure. While for coated yarn, we assume Q equal to 0.53 to reproduce the softening and then also the plateau. And what we obtain is represented here. Here, the red curves are that given from simulations. And so we arrive at this point, and then we have failure, and failure is due to the bonding at the interface. Here I plot alpha, the damage parameters, versus the position y. And we have that the bonding starts in the upper side and then evolve downward until we reach this, the situation given by the curve number 3. And then after this point, the bonding of the wall interface occurs. And so we arrive at half. We have this situation given by the curve number 4, where alpha is equal to 1 total damage in the wall interface. Well, in the case of H equal to 50 millimeters, we have again the brittle behaviors, but in this case damage localized in the yarn in this point, right above the sample, the matrices, as observed also in experiments. And in the case of coated carbon yarn, we have this response which capture pretty well the experimental curves. The numerical curves are quite close to the experimental one. And what happened is that in both these two cases, H20 and H50, we have at softening the evolution of damage from the upper side toward the lower side, so moving downward, until the damage becomes practically homogeneous, constant through the interface, and then from this point on it evolves homogeneously, and this evolution corresponds to this horizontal plateau. And both in the two cases, here we have that damage evolves downward, becomes practically homogeneous, and then evolves. And so going to the conclusion, FRCMs reinforced with dry yarns have shown brittle behavior, and two different collapse mechanisms, by slippage or by yarn breakage. The coating has contributed to increase the system strength, and indeed the peak load was increased, and has conferred ductility to the system. Regarding the modeling, this phase field variational approach seems to be quite promising, since it is able to reproduce many aspects of this problem, so it reveals a great predictive capabilities. And another advantage of this model is that it is based on few constitutive parameters, which are all them are inside the energy, and which can be related in a quite simple way to specific material property, which can be measured from experiments. And this is all. Thank you.